So we'll start this session with a multi-user posture and gesture classification for subject-in-the-loop applications. And so we are with Joanna Luberadzka, I'm sorry if I misspell your name, and your Giso Grimm, and it's been written with Volker Hohmann too.
Yeah. So thanks a lot for the introduction, and we try to give a presentation of our work on classification of postures. So there was some discussion on how this is related to Linux audio, and you will see why we think it is during the talk. So the main inspiration of doing automatic classification of postures and gestures for us was coming from different applications. So we always had an application in mind. And maybe the most important application, to some extent, was in hearing aid research, because that's the field we are coming from, and it's our daytime work. So at in hearing aid research, there are several things which we would like to do with classification of postures and gestures. So one thing is we would like to identify gestures, or postures, which are related to a listening effort. So just imagine a situation in a cafeteria or something where you want to listen to someone. If you cannot understand a lot, then you try to lean forward or to try to get it better. And this can be done in several stages. So one application is evaluation of hearing aids. So you have hearing aid algorithms of different kind, different processing strategies. And for all these different kinds of hearing aids, you look at the behavior of the subject, and then you measure it and rate the hearing aids. But you also could imagine a rather advanced application where you have a hearing aid itself, and this hearing aid classifies the situation of the posture of the user. And just by looking at on several measures, so partly on the posture, but also on other measures, you can identify whether the subject has a low effort of listening or a little effort. So what's one of the main applications? And for this, we define some states, some postures which might be relevant. So something like a more relaxed posture, sitting straight, leaning forward. And also you can identify someone just while they are talking. So usually they are doing gestures while talking. But then we have more interesting applications maybe in some, so it's more applied to acoustics and art. So we would like to create an interactive art installation, so an audiovisual installation, where the subject can contribute on this art. And so the idea is we would like to inspire the subjects to behave, to perform some kind of dance within this installation. So we have some kind of feedback loop to the subject. For this, so what we had before, so it was an art installation related to water states or water appearances. I will come back to that later at the end of the presentation. So we have different states, something like lake and ice and boil, so different appearances. And we attributed some, in this case, more gestures to these states. So they're not really related to the content of this, but it's just to distinguish between different gestures. And we would like to distinguish between those and identify them. And another application, which is even more fun maybe. So we would like to have a party system. So we would like to control the light of a party. So the lamps, like the disco lamps, based on the individual dancing behavior of the subjects. So we have very many dancers on the stage. And some of them are dancing, some others are just standing around. So if you go back here, you see some are just standing around, or this one. Some are having a beer, I think she is having a beer. And these are just standing, some others are rather dancing a lot. So every one of those should have an individually controlled light system. And here we have some states which we would like to distinguish. So it's dancing, drinking a beer, or not standing, dancing, and extreme dancing, and doing some kind of specific motion behaviors or gestures. So what's common to all of these three applications is that we have some kind of subject in the loop. So it's kind of feedback loop. So we know that the human behavior, the motion behavior, depends on the audiovisual environment that we are in. But then we have this subject in the middle, and we have some kind of apparatus which tries to control and to stimulate certain behaviors. And by doing this, by closing this loop, we might be able to control the behavior in some sense. Also, we might utilize this to measure the adaptation of the subject to this feedback loop. So that's the main point of this classification method, actually. What is special about this is we are looking at 2 points are important, actually, in this classification approach. One is we would like to describe states, so like this motion states or postural states. And we would like to look at mixture states. So we don't want only to classify and identify certain gestures, but wouldn't like to make a decision, but we would like to estimate it's, let's say, 80% sitting straight and 20% maybe sitting relaxed, something like this. So we need to look at the state probabilities. And we also want as you have seen in these art and party applications mainly, we also want to have a multi-user system. So it's not only a single user, but rather multi-user. So we are looking at some kind of probability matrix for every state and every object which we are observing. But this is mainly the most important difference to other conventional systems, which rather are used like for instrumental control. For example, you are rather trying to control some instrument, so it's a direct gesture which is directly extracting features to control instruments or to steer your smartphone or whatever. So this is the main difference to that. And that's the reason why we started to do our own stuff. So it's always a question, why not use existing stuff? So we started to do our own because we thought this is a way which is more feasible for us. So this is roughly the system which we would like to present you. So this is also at the same time it's the overview of this presentation. So we start with, very briefly, I go over the hardware setup and the tool chain which we applied. And then in the next step, we did some kind of point cloud processing and separating of the objects. And doing then some kind of classification, Joanna, where you talk about all the theoretical and hard stuff of mathematics of it. And also some fancy tools of optimizing the feature space. We show some results on the performance of these classifiers, and in the end, if you have time, I will show you some applications of it. Yeah, this is the lab facility which we have recently set up in the last couple of years, where we trained the system. So it's called the Gesture Lab. I just go briefly through it. We have very many loudspeakers, so it's a nice, fancy, but still small setup which we can control easily with audio and vision. And we have lots of sensors, mainly for doing this. Measuring features, so we are mainly using the Kinect depth camera here. But we are also using cameras to track the subjects while we're doing the training. You will see that later. But the interesting part is most of this lab is powered by Linux audio tools, and mainly it's free and libre open source software. And just after this talk from Paul before, so our focus is on the open source component, because in science, it's really an important aspect to have the reproducible of science. So having the code in some kind of quality measure, so we can store the code somewhere, and we know that this was the way it was done in this experiment. So it's reproducible in some sense. So we know what's happening here. Or even if we don't understand it, at least we have the documentation of it. And there actually, in this way of classifying posters and gestures, we have 4 stages. So the workflow is split into 4 stages. We start with the recording of features for the training. So at some point we have to define the labels of the classes which we have, and we record some subjects. So in this case we had 10 subjects going into this lab. We were recording the states of these, or the motion behavior of those subjects in these labeled situations. For that, we used different tools. So we used Jack for the timeline. So we really appreciate the timeline and the Jack transport control features. They're really great. We abused, actually, I should say, OpenMHA to do the Kinect processing, the point cloud processing and classification, actually. So it is meant to be some kind of audio signal processing tool, but we just created some kind of driver for the Kinect. So having an image, that's a depth image, we have some kind of width times height times depth. And this is just a different kind of block-wise signal processing. Doesn't really matter whether you use audio or anything else. And then we use a tool which we showed 2 years ago in Mainz. It's Tasca. Actually, we abuse this tool. This is mainly a virtual acoustic simulation tool, but we abuse it just for data logging and some timecode generation, which is actually all the timecode generation is based on Robin's tools with the LTC stuff. And then the next stage, we did the labeling of the feature vectors. For that, we used we abused the tool. We used Ardor, just using range markers to put labels on the timeline. So maybe it's strange you have this huge and very complex tool of Ardor, but we still just used it for putting the labels. And we were using Blender abusing Blender to display the video, to label the states in the videos. For the training and optimization, we used Octave. Also at some places we use MATLAB, but everything works also with Octave. And in the end, we have the final application where we just have this OpenMHA for this classification and point cloud processing. And of course, then depending on the application, we have different ways of controlling and different things which control the audio, video, or whatsoever. Yeah, so you see it's a nice mixture of free and liberal open source tools, which we have here. Mostly we use them because we just like to use them, like Ardo. I really appreciate Ardo, but I mean, we wouldn't really need to use it in this lab, but I like it to use it personally, so that's some personal stuff as well. How does it work? In the point cloud processing, we get this image from the depth camera, from the Kinect, and we have to look at something. So we have lots of problems with this point cloud. The depth information is not very noisy, so especially if you have like curly hair like me, you have lots of black dots where you cannot measure the depth, also at edges, or if some things are moving. So we have to do some kind of handling of this noise. So here's also, I mean, that's not me, but it's someone else with curly hair. But after this noise reduction, we get some kind of stable image of the depth. At the next stage, we have to remove the background. So at some point, we have to have a scan of the environment without subjects. So we can remove all the background of it, and only the important objects remain in this setup. To group it into objects, because I mean, we want to have these identified as two different dancers, in this case. We just need some kind of edge detection algorithm. And we are using a flood fill algorithm then to fill these objects and identify the objects belonging to one set of points, depth points. There are some tricks involved in it. Maybe I just skip this, but I mean, there's always a question. If you have objects on one frame, it's just depending on random noise, whether this object is first or that object is first. So we have to, from frame to frame, we have to identify and rearrange them in some way. So if you have many dancers, you don't want to switch the number of objects all the time, because otherwise you cannot estimate like velocities and stuff like this. So you have to do some kind of tricks to reorder them from frame to frame. So we define some kind of temporal object coherence, which is mainly it's the size of the objects and the distance from frame to frame. So size changes and distance changes. And we just try to diagonalize some kind of this coherence matrix to optimize the order. This works quite well. Yeah, so we have this point cloud for every object. So now we split this into objects. We have only the points of one object, so we look at different things. We have features which are operating in the global space. So we have the global coordinate system where we have the center of the object and also some rough measure of the orientation of it. And we need this mainly for the spatial reproduction in the end. So we don't really need the global position for the classification of gestures and postures. Then we have object-based measures, like the size of the object, the dimension in different axes. Then we can split these point clouds into segments, so some kind of percentile analysis. So we would say this is the first 25% of, or the first 33% of points. This is then the next 33%, and this is the rest. And we can also calculate like weighted average of these segments to calculate something which is roughly representing the hands or the feet. And at the last stage, we try to calculate like velocities or temporal derivatives of these segments and weighted averages to identify something like which is more related to gestures. So we have this distinguishing between the postures, which is more static stuff, and the gestures, which is dynamic. Yeah, and with this, I would like to hand over to Joanna.
Fine? Yeah. Okay. So now I would like to make a short introduction to the Bayesian classification in general. So maybe I hope you will find it interesting, as I do. So this bias rule, you have probably seen it on statistics lecture or whatever. Yeah, but so this simple formula gives us a nice framework to solve many classification tasks. And I will go straight into the example with classification of a fish. So let's say we take a fish from a lake or from a sea, and we want to classify this fish based on some measurements. So okay, there might be a lot of measurements done for this fish, but let's say right now that we just measure the length and the width of the fish, and based on these two measurements, we want to classify to which species this fish belongs. And so in case of these two variables, so width and length, we would have just two entries of this feature vector, like f1 would be length and f2 would be width. And let's say we have four classes of fishes we want to distinguish, like, I don't know, salmon or a shark, a bass, and something else. Okay, and then we have this Bayes formula. And what we need to solve such a task is first we need the so-called prior probability, which tells, so this P of class C1, let's say, so prior probability of a salmon, which tells us how often does a certain class appear in relation to other classes. So it might be that, for example, we know that a population of one fish is bigger than the population of the other fish. So this is like a prior knowledge about this population of fishes that we have, and then the prior probability of the class of the fish with a bigger population would be bigger than for the other class. So here you can see that this C1, C2, C3, C4, and they are all equally likely all these fishes would be equally likely to be taken from the lake. But anyway, so this is this prior probability that we need, and then we need something which is called class emission probability or noise model or likelihood. It can have different names, but in general it tells us what are, for a given class of a fish, so for example for a salmon, what are the typical variations of a given variable. So what kind of variations of for example length we expect from a salmon or from a shark or whatever other class. Yeah, and this is represented as probability. So how likely it is that this fish has a length of 1 meter. Yeah, and so having these two probabilities, we can solve a task and obtain a posterior probability, which tells us that given a fish, given that we have just taken a fish from the sea and we have measured the length and the width of the fish, how likely it is that it is a salmon, and then how likely it is that it is a shark, and so on and so on. And then for each class, we get using this formula, we get these posterior probabilities, which, and as you can see here, this is the winner, so it will be probably, I don't know, it can be a shark. Yeah. But now, like going to the machine learning problems which we have. So, how do we know what is this class emission probability and this prior as well? So this is something we can learn from the data, which means that if we have like 1,000 examples or more examples of a shark or of one class of these fishes, we can learn from these examples what are the typical variations of length or width in the class. So this is what training is all about. And then testing the classification performance, testing our classifier. It means that then we take again a bunch of examples of a given fish, and then we see what kind of output does the classifier give us, and knowing that this is a salmon, and for example the classifier tells it's a shark, so we know, okay, this was a failure, so we doesn't count it as a yeah. So then the classification performance is probably worse. Yeah. Okay, so that was the introduction. And now going back to our methods, what we are using and assumptions that we make. So first we make, because here I was talking about any probability distributions. It can be whatever. And here we make an assumption that the data is normally distributed. So if we have just two variables, then this is the two-dimensional Gaussian distribution, which would, it can be any like it can have many more dimensions, but to see how it looks like in more dimensional space, then you have just two variables here. So this is our first assumption. The second assumption, more important, is that we assume that the features, so these entries of the feature vector, are conditionally independent. And so here we have two examples. These features are conditionally, like these features are dependent, and these are independent. And it means that, for example, in case of a width and the length, these two features are dependent, probably because we know that if a fish is bigger, then the fish probably will be also broader. So there is some kind of a correlation between these two variables. And so, for example, here this would be like, let's say we measure length of a fish, and we also measure then, I don't know, something completely different, like a number of dots on the fish, which could have nothing to do with the length. And then they are independent, and this is our assumption. So it's a very strong assumption, I would say. But we can do, to make it work, we can do a couple of things. But okay, so this side. So first, why do we make this assumption about independent variables? So this is important. So maybe not going into the details, but instead of modeling the whole multi-dimensional Gaussians, we just, for each feature, have one-dimensional Gaussian, because there is a, instead of this multivariate distribution, there is a univariate, the multiplication of the univariate distributions here. So anyway, this means that instead of modeling the multi-dimensional Gaussian with a huge covariance matrix, we just, for each feature, we just find, and in each class, we just find the mean and standard deviation of the data, and this is already what characterizes the one-dimensional Gaussian, so it's kind of a simple problem to solve. And here, here you can see, for example, let's say this feature is the length, so we can see this is how the length is distributed for salmon, and this is how the length is distributed for shark or whatever. And so probably there will be, this will give us a nice separation between these two classes if we measure the fish. Okay, so as I said, so why do we do this? Because it's less, we have to compute less than in case of multivariate Gaussian. But the problem is that it might not capture the dependencies between the data. So, but we can do a couple of things about it. So yeah, I will anyway just go into the details right now. But so it includes low-pass filtering and selecting the features. We have a method for selecting the features to make them relevant. Okay, so first thing what we do is that we low-pass filter the recorded features. So if we imagine that this is, let's say this is one feature which is recorded by the camera. So it is quite noisy. So let's say this was a transition. So here the subject was doing one pose, and here the subject was doing the second pose. So these are our labels for these features. And as you can see here, if we take this, like this unprocessed signal, the Gaussians modeled based on this signal are broad and they overlap quite much. So probably the separation wouldn't be enough here. So then if we low-pass filter, then it looks much better. So it reduces the variance in this signal, so there might be a better separation between these two classes. But of course, if we filter too much, then it doesn't allow any variance in the data. So it's basically also won't be, the classes won't be separated either. So the whole thing is that for each project that we have to find adjust the filtering constant to make it as make the classification performance as good as possible. Okay, so and this the second thing we do is that we from the whole feature set we just pick the features which lead to a better classification performance. So what we do, this is the method we first for each feature in this feature set, this is our feature set. Giso was already talking about, like different features of a person doing some gestures or poses. Yeah, so for each feature we train the classifier using only this one feature, and then we test it using new data, and we compute the classification performance, and then for each feature we do the same, and then we sort them according to their classification performance. So these are these sorted features. So this feature has the best individual, or its individual classification performance. And then, so we have these features in the sorted feature set, and we create a new, like a selected feature set. I called it something, selected feature set, and then we keep adding new features to this selected feature set, and we keep checking if it leads to higher classification performance than it was before. And if it does, then we keep this feature, then keep this feature in the selected features set. If it doesn't, then we throw the feature away. So, for example, here, these features were taken to the feature. That there are small stars here. These features were taken to this selected feature set. This one was also didn't cause the increase in the classification performance, so it was discarded, and so on, until we have a smaller feature set. Yeah. And yeah, maybe I think it's already quite late, so I won't go into the details. But the main thing is that without this whole pre-processing, the classification performance is, at least for 2 projects, at the chance level. So it basically doesn't work. So this selection of the features and also choosing the right filtering constant is crucial for this naive, because I didn't mention, so it's called naive Bayesian assumption if we assume the independent features. Yeah, and for each project it's also different, because the pace of the changes of the postures are also different for each project. Okay, yeah, and this is the results in a more digestible form. So time, and 5 different classes. This is, you can see which class was. So this red line indicates the true class. So here it was stand, then it was drinking beer, then it was dancing, extreme dancing, and windmill. Yeah. The colors indicate the posterior probability found by the final classifier with all the pre-processing. So as you can see, it worked quite good here. I mean, for most of the, in most cases it was classified correctly, right? Because the highest posterior probability was for the true class. This confusion matrix is just the average over time. But we can see here the confusions. We can see a bit better. So, for example, like this windmill was confused with extreme dance, and extreme dance with windmill, and for example, dance with beer, and so on, so on. So there were some confusions, but in general, yellow diagonal means good result, and. And in case of all the projects, it was all of these projects. It was was quite good. Yeah, and yeah.
So this brings us back to the applications. Back to the applications is, so as we showed before, this was the structure of our system. So we have the depth camera, the preprocessing, the feature extraction, and the final classification. But now what do we do with it in a real thing? So this is one application, which is our visual installation, which I mentioned before. So we have some more blocks here, which you see, which I show you in detail. So first we have some kind of artistic process. So we have some kind of composition where we we describe different appearances of water. So we assign a video snippet, which is looped always, and some sounds and also some colors to these states, appearances. And these are the things which we would later we would like to use in the mixture of it. And then we have our labels, which you have seen before. So they are the postures or gestures which we assign to the same states, which we would like to classify with the classification algorithm. And then we do some kind of spatial processing. So we do the spatial processing comes later. So we do the mixing first. So we just use the probability, the posterior probability to mix the different states. So in the ES case, we just use this posterior probabilities as an input gain for mixing. So we just say the probability of, let's say, state 1 is 50%. So we take 0.5 multiplied with this video, and then 0.5 multiplied with the video of the second state in some kind of mixture states. And then we do this for all these different objects. So if we have, let's say, 3 visitors in this exhibition, we just take the probabilities of all these visitors. And then we have one mixed, like video or sound or whatever color, for every visitor in this installation. Yeah, so object always means visitors in this case. But I mean this. And in the end, we do some kind of spatial processing. So we would like to reproduce this to be perceptible by the listeners. So we need some kind of different rendering. So for the audio, it's easy if you just use some kind of panning. If you use ambisonics for that, we have an ambisonic system. For the video, we would like to have always a full screen filled with image. So we are using some kind of Bayesian mixing model. I mean, I don't want to go into details, just assuming some kind of spatial distribution of these objects, and then you can create some kind of mixing matrix which gives you a full image for every point of the screen. And for the light, we just have some kind of fixed lamp array, so we just use some kind of raised cosine panning for the light, so we can have moving objects even with a fixed lamp array. Yeah, and then in the end, we have just our reproduction systems. So this is what it looked like in some kind of installation we had. So this is actually not exactly the thing which we have here. So here we had like a cube audio system and only a few lamps, but it was generally the same method, same installation. So the visitors came here to this cube, and they were doing some actions, which were shown before outside this cube. And it also it had some kind of exhibition state where you could, in real time, you could follow the probabilities and all these visualizations of all these internal states of this classifier. And yeah, in the party application, which is maybe more fun, but I think the other thing was also fun because I mean, sort of going back here. So even like 80-year-old people coming with their what is it called, barely able to walk, they were starting to jump, and even if just small jumps, they tried to create these states. So it really was motivating the people, any people of any kind, just popping in from the street. Lots of people just started to move, and they were really inspired by the system, seeing this interaction and the reaction of the system on their behavior. So actually, it was some kind of success in that sense. Here, it was another system. The setup was quite similar. I mean, it was essentially the same. So we just had this classifier again. But we had also some more audio processing. So that's the reason why I would like to show some details here on the audio part, which you see here. So maybe this is the strongest link to Linux audio. Because here we would like to use like this artistic process of defining the colors of the lamps is also controlled by the audio signals. So if you have party, would like to get some kind of sound sources. We have music from records or whatever. And we extract some music features from this. So we're having some kind of beat structure, just some kind of low pass or narrow band, low frequency content, and doing some kind of tracking of this for extracting beats. This will control the light in some conditions, I mean, as you would expect for a dance floor light system. And we are also using some kind of inter-channel coherence function, just showing some kind of diffusion or complexity or spatial complexity of this sound. So if it's just diffuse sound, then it should give a different kind of light than if it's just some kind of focused sound. And yeah, so it's some kind of algorithm doing extraction of this diffuseness. And then we are using, for this dance floor application, we are using spatial upmixing. So we are taking the stereo source and rendering it like the coherent components, which is more localized. It's rendered to a stereo set, which is in the front of the subjects. Or not a subject, so it's in the front. And we have the incoherent components rendered to the back with some kind of source widening using the algorithm of Franz Sutter. And the whole system was slowly rotating, so you don't have really a clear preference of any direction. So and using this spatial upmixing and the diffusion really created a sound field which was quite nice on the whole stage. So on the whole dance floor, you had a very complex soundscape. Yeah, and then in the end, we applied this light system. We had 2 rings of lamps, so we had one 8-channel lamp system going from top, rather with broad lamps, creating some diffuse light. And we had the narrower beams coming from the sides. But with these lamps, we were able to more or less track the subjects and put the lights on the subjects. So this was our composition. So we had different effects of the beat structure in the different states and also different effects of the coherence on the states and different color sets. But yeah, so basically it was lots of fun to do this, to implement it, but also it was fun for the dancers at the party. But we have to admit that despite having a very high classification performance in the lab, it was not that good in the final application, so on the stage. So that was a bit of a problem, which as a conclusion we might take that we need more training during parties and not only in the lab. So that's our main conclusion of this talk, and thank you for listening.
All right, thanks a lot for your talk. We have some time for questions. Are there questions in the audience? Yes?
Maybe I missed something there, but where are you going with this? Is this going to be some kind of, interpret gestures for what? What kinds of applications do you see in the future?
Well, I mean, as a hearing aid researcher, in my daytime job, so mainly it's a classification of gestures and postures for, evaluating and hearing aids, and also doing this in real time. So now we are using this Kinect-based point cloud processing, but we could also use different sensors, like acceleration sensors in the device itself. So we could guess or estimate the same postures from. Well, we don't want to focus on gesture control. Doing gesture control is something different. So that's the main. There are tons of tools for doing gesture control. So doing explicit gestures, identifying gestures with some systems. You could imagine like a beamformer, just I'm pointing in some direction, the beamformer goes there. This is not what we want. We rather want to have some more subtle system, so we just identifying that I'm in bad mood or whatever, I'm having some kind of certain behavior, and I need to adjust slowly the signal processing strategies to my current state.
Or maybe, for example, if a person is moving his or her head a lot, and this behavior is recognized, and the signal processing in the hearing aid could be adjusted to this behavior, to the head movements, for example.
Yeah. So if you have a very narrow beamformer, for example, but you are trying to orient and looking for new sounds, and you are moving your head a lot, you might just shut down the beamformer and just switching to omnidirectional processing. So this is a more scientific and applied part of it. But we started with the installation and fun side of it.
All right, thank you.
Yeah, thank you.